Aloha, welcome back to General Pharmacology. We'll move to PowerPoint slides, see how quickly we can slog through these. All right, so you guys know that Pharm 203 has a math section, and that we've been very proud of that math section. However, we're also teaching pharmacy technology or pharmacy technician course here, and something they're doing with our pharmacy technicians is making their math skills, they're requiring their math skills to be even better than what we've been teaching previously. So I wanted to go through some slides of how complex pharmacy calculations can be. And so today we're going to try to make something simple of something very complicated, not only for our pharmacy technician students. I think that our pharmacology, Pharm 203 students eventually should have this kind of math education. And so eventually we're going to pull this into all the pharmacology teaching that we do on this campus. But it took me quite a while to put these together. I thought this was very difficult, especially for a single board question. And the key to this is there's a lot of board questions all in one. But before we get to the hard part, in the old days I used to just call this How Red Is the Kool-Aid. And the last time I explained this, I used Kool-Aid, but being in Hawaii, I thought we'd use something a little more fun. And so you guys might have seen this. This is Hawaiian Sun Luau Fruit Punch. And you don't drink this punch. It's a liquid. It's a concentrated liquid that you put into, that you mix with water to make juice. Now, when you have kids, you don't have to mix it up exactly perfectly. And your kid's like, oh, well, it's too sweet or it's too watery, and you're like, just drink it. But in pharmacology, your mixtures have to be absolutely perfect. And so for the purpose of this lecture, to impress our children, we are going to measure out the fruit juice perfectly, as if we're doing something in a pharmacy. And so if you look at the directions for Hawaiian Sun, they explain the directions in ratios. We're starting out this way because I think a lot of the teaching about ratios is confusing and sometimes incorrect. And so the best way to describe that is quite simply with our Hawaiian Sun fruit juice. And so the directions will be explained in ratios. They don't call it ratios. They'll say mix 1 part concentrate. That's what this is. This is the concentrate. With 5 parts water. And then you'll have the perfect mixture of juice that they recommend. And this is something that you'll see in a pharmacy. They'll have some concentrated form of a drug, and we'll mix that in sterile water to get exactly the concentration that we want. But we're not in the pharmacy yet. We're still in the kitchen trying to make juice for our children and putting way too much thought into it. And so it's real simple. If you take 1 cup of this concentrate and mix it with 5 cups of water, well, you'll have exactly the perfect solution. Maybe you want to make more than that, and so you think, oh, well, if I want more than that, I'll take 2 cups of concentrate because we just doubled the recipe. You guys know how to double a recipe. It's really simple when you're making juice or cookies, and then it gets into pharmacology and everybody starts freaking out. And so, well, gee, if it's 1 part concentrate with 5 parts water, well, if you take 2 cups of concentrate, you'll need 10 cups of water. Or maybe you want to make a half batch, use a half a cup of concentrate, and then use 2.5 cups of water. You'll make up the perfect juice. And so maybe if you just want to make a little teeny tiny amount, you'll take 1 milliliter of concentrate and mix it with 5 milliliters of water. And so as you watch, you're like, well, that's really, really simple. Why are you doing all this? Because it gets more complicated. All right? So you guys know how to mix up juice. All right? It's fine. All right, here's where I want to make things a little bit more complicated. Again, they explain the directions in ratios. They tell you to mix 1 part concentrate with 5 parts water. But I'll tell you right now, if you take 1 part of concentrate and 5 parts of water, you actually have 6 parts of solution. That makes sense. Gee, if I take 1 cup of water and if I take 1 cup of concentrate and I add 5 cups of water, you're going to end up with 6 cups. Right? And so this is important to remember when we're talking about these part-to-part proportions. especially we have two liquids here. We have one liquid that we're adding to another liquid, and so I want you to see that they're going to describe the ratio as 1 to 5. And what that is a part-to-part proportion. All right. But remember, what is our final solution? Our final solution is 6 parts. All right. So if we had 1 part with 5 parts, that's the directions. We end up with 6 parts of solution. And so one way to describe the ratio would be 1 to 5, and when we mix it up, that's 1 part for every 5 parts, 1 part of 1 part of concentrate for every 5 parts of water. And that's a proportional ratio. However, the ratio can also be expressed as 1 to 6, meaning 1 part concentrate in 6 parts of the final solution. And this is what I see going on not only in the teaching of ratios, in a lot of places, but I see this also in the pharmacology books. Now, where we talk about this, I don't think that the difference between 10,000 and 10,001 parts is that big a deal. But this is something I want you to keep in mind when you're thinking about ratios. Because something they tell you about ratios is like, oh, if it's 1 part concentrate to 5 parts water, oh, well, how would that be as a fraction? And you'll say, oh, well, that's 1/5. That's not correct at all. All right, so if you mix 1 part concentrate with 5 parts of water, you have 6 parts. That means 1/6 of the solution is concentrate and 5/6 of the solution is water. And so when you're looking at ratios, kind of getting confused, I want you to think about this right here. And look at what's happened. We've had 1 part with 5 parts. That's 6 parts, and so that's where the denominator of the fraction came from. And then the 1 part and the 5 parts, they become numerators, all right? And so the way to describe this concentration is 1/6 of the final solution concentrate, 5/6 of the solution is water, and they'll describe that as a 1 to 5 part-to-part proportion, all right? And so that's something confusing that I've come across as they teach ratios in pharmacology. Well, that seems kind of complicated, especially talking about juice. So let's actually make it simple. Let's use something really concentrated, and that's a powder form, all right? And so here we're going to make passion guava juice with our Hawaiian Sun packets. And here I've taken the liberty of using 1 liter rather than a quart. A quart's like 943 milliliters. And we want to just go ahead and mix it with a liter of water because we use the metric system in pharmacology. And so, look, it's real simple. You take 1 liter solution, it's a bottle about that big, you add a packet to it, well, then you have a liter of fluid, and it's that perfect juice mixture, all right? So 1 packet in a liter of water. Wow, that's really simple. Why are we even talking about this? All right, well, something I want you to see is that that packet contains 100 grams, all right? So then the concentration of juice is described when we add 100 grams of the powder to 1,000 cc's of solution. And so when you see 1 liter and the rest of the units are in milliliters, which is the same thing as cc's, just go ahead and make the leap. 1,000 cc's. All right, well, if we take 100 grams of powder and mix it with 1,000 cc's of solution, what we have is a 10% weight to volume concentration. And so this is how the instructions will be in pharmacology, in a pharmacy. This is the instructions on a packet. 1 packet in a liter, all right? That's what this says. 100 grams is in the packet, and we're going to put that in 1 liter. We're like, oh, that's really, really simple. And then we go, oh, well, 10% weight volume, oh, that's really scary. And so the easiest way to do that, and we're going to show you that in a second, is that percent, oh, that's just the same. You can just take that percent and make that grams in 100 cc's, all right? And so remember, a gram of water weighs, a gram of water is 1 cc. 1 cc of water weighs 1 gram, all right? So grams in 100 cc's is a percentage. And so that's something I want you to be able to remember, and we'll go back and show you this chart in the book. So wow, putting 1 packet in 1,000 cc's gives us a 10% weight by volume concentration. And so many of the pharmacy calculations that you'll do, they won't say, oh, put a packet in a liter, right? They'll tell you this right here. And these instructions are the same thing, because if you're going to make a 2-liter bottle, you put 2 packets in it, all right? So if we take a 1-liter bottle, we'll put 1 packet in it. That's 100 grams. Okay, but here we have a 2-liter bottle. All right, well, that's twice as much as 1 liter. So it makes sense if we're going to double the recipe, we'd put 2 packets in it. Great, that's really simple, all right? So if we're going to make double the amount, then we're going to need double the amount of packets, all right? If we're making a half a batch, we'll use half a packet, all right? And so that would be a 50 grams in 500 cc's. But remember, the concentration remains the same as a 10% weight by volume. All right, percentage, 10% weight by volume, weight in volume. All right, so really simple to understand when we're talking about juice. And again, we're trying to make the juice that perfect flavor, because that's what we have to do in pharmacology. Our concentrations have to be perfect when we mix these up. So in pharmacology, concentrations are also instructions on how to mix this stuff up. And so when we see, oh, put a packet in a liter of water, that sounds like an instruction, all right? When we see 10% weight by volume, that doesn't sound like an instruction at all. All right, that looks confusing. And so that's why we're going to go through this, try to make these connections, all right? All right, so on your American Society of Hospital Pharmacy Technician Certification Review and Practice Exam electronic form of the book, we're on page 12, and there's a table here that says Standard Intravenous Solutions, and I wanted you guys to be very well aware of that. NS is normal saline. It's 0.9. Please always put the leading 0 on your numbers when you write this out. And when you want normal saline, please don't write out 0.9% sodium chloride. Just write normal saline. All right, it should be, this is how it's known, and this is how it's also written, okay? So it's much safer to write these sorts of things than to write this stuff over here, because this gets confusing, because people lose track of decimal points and leading zeros, and this can lead to very bad outcomes. But that all set aside, a 0.9% sodium chloride solution, we can take that 0.9 and say, oh, well, that's 0.9 grams for every 100 milliliters of solution, because remember, a percentage is per 100. 1 per 100 is 1%. And a milliliter weighs a gram. And so that's why when we see a percentage solution, we can just take that percentage and say, okay, that's the number of grams in 100, all right? And so it's confusing at first to think about it, but I want you guys to be really well aware of this. Even for those of you who are not in pharmacy practice, having this understanding is very important, because not very many people understand this kind of math. So again, 0.9% sodium chloride solution is 0.9 grams for every 100 milliliters of water. And so when we see 0.9, not only is that a description, but it's a description of the solution, but that's also instructions on how to mix this up. So when we see 0.9% sodium chloride, that means we need 9/10 of a gram of sodium chloride for every 100 milliliters of solution. That's what this 0.9 tells us. Right, well, half normal saline is half of that. If we want to add some free water to our normal saline, then we're going to use half the amount of sodium chloride. And so the 0.45%, we can just say that's 0.45 grams. We can just translate the percentage directly to grams, and we know that that's in 100 milliliters of water. Quarter normal saline, I wish there was more quarter normal saline hanging around when I was in practice. We didn't really use this much. We don't see this much. 0.225% sodium chloride, and we can take that 0.225% and take this over to 0.225 grams in 100 milliliters of water. Same thing with dextrose. Dextrose is glucose, a form of sugar, and so 5% dextrose in water is 5 grams of dextrose in 100 milliliters of water. 10% dextrose is 10 grams in 100 milliliters of water. And then here we have dextrose 5% and normal saline. That means there's both 5 grams of dextrose and 0.9 grams of sodium chloride in 100 milliliters of water. And when we redo these slides, we'll make them big and easier for you to see on TV. But this is what I have today. Oh, good. There it is. There's the bigger slide. All right, so we went through this. Again, we'll take the 0.9% and we'll just say that's 0.9 grams in 100 milliliters of water. And so when we see a pharmacy percentage, we can take that percentage and say that's grams in 100 milliliters of solution. All right. And so that's what we've been working on is here in the middle, weight in volume. So we've talked about 0.9 grams of sodium chloride in 100 milliliters of solution. And that's a weight in volume percentage. But you'll notice that it doesn't matter whether it's weight in weight, weight in volume, or volume in volume. It's the 1 unit over 100 units. And because that makes sense as a percentage. And remember, a milliliter weighs 1 gram. A milliliter of water weighs 1 gram. And so that's why our numerator in this is either going to be grams or something that weighs a gram, like a milliliter. And then our denominator in this is going to be 100 grams or 100 mils, whether we're talking about weight or volume. And the stuff that we just went through on the previous chart is weight in volume. So when we see that percentage, maybe they'll bother to put the W/V, meaning weight in volume. And so we're going to do some calculations about concentrations. And again, when we express it as a percentage, it's 1 over 100. All right. The concentrations get a little bit more complicated here. We have grams per milliliter of solution. And so if we have a 1 to 200 solution, that means we have 1 gram of drug in the 200 milliliters of solution. So 1 to 1,000 is 1 gram of drug in 100 milliliters of solution. You'll see epinephrine dosed this way. If it's cardiac epinephrine, you'll see it like this. If it's epinephrine in a local anesthetic, you'll see it like this, 1 gram of drug in 10,000 milliliters of solution. Please do not confuse these two. They look alike, but there's a big 0 between the difference of them, between the two of them. So again, a 1 to 1,000 concentration ratio is 1 gram of drug in 100 milliliters of solution. 1 to 10,000 is 1 gram of drug in 10,000 milliliters of solution. And not only is this a description of what you see in the package, but this is also instructions of how to mix things up, just like 1 packet for every liter of water when we started out with juice. And so don't forget, these concentrations are not only descriptions, they are instructions on how to mix things up. Look, when you had the juice, it just tells you 1 packet for every liter, or 1 part of the concentrate to 5 parts of water. And so you then decide if you're going to double the recipe or quadruple the recipe, or you're going to make a great big thing for a party. You have to do the math for the different volumes that you want. You have to do that when you're mixing up packets of juice. You have to do that as well in pharmacology in a pharmacy when you're mixing these things up. All right, so since today we have been focusing on things that are ridiculously complicated in medicine, I thought we would go through the most complicated equation, the most complicated math that we see in the Pharm Tech Review. And so here, we're going to mix up 1.5 liters of total parenteral nutrition. People who can't eat for a long time, maybe after a surgery for whatever reason, we have to give them nutrition IV, and that's what TPN is up here at the top. And I think I've rewritten this in something easier to read, but this is straight out of the book. And so we want 1.5 liter of solution, and we want 17% dextrose, 3% aminosin, 2.5 liposin, sterile water we want the solution to have, and this really doesn't belong here in the question because we're not going to put 1,500 milliliters of water in this solution, and so I'll take that out. However, we want 15 milliequivalents per liter of sodium chloride. We want 15 milliequivalents of potassium chloride in the solution. We want 10 milliequivalents per liter in the 1.5 liters. We want 10 milliequivalents per liter. That should only have one slash there. And then the multivitamin, 10 milliliters per day. 1.5 liters of TPN over a day is plenty. So I'm assuming that this is one bag of TPN per day when we do this calculation, because the book didn't really make that clear. All right, well, this is what they want, and this is what we have. We don't have a 17% dextrose solution. We have a 70% dextrose solution, and this is like mixing up with the concentrated juice. We have concentrated dextrose and concentrated aminosin and concentrated liposin. We have concentrated sodium chloride, concentrated potassium chloride, potassium phosphate, and magnesium phosphate. And you can see these little recipes here. And so already this is getting really complicated. And so in the middle of the night, I was reviewing the math with the Pharm Techs, students, and they said, well, will you do this equation for us? And well, not in the middle of the night. But I will get up in the first thing in the morning, and I will sit down with my Excel spreadsheet, which they will not have when they take the boards, and my PowerPoint slides, and we will answer how much of each stock, how much fluid are we going to add of the concentrated dextrose, the concentrated aminosin, the concentrated liposin, the concentrated sodium chloride, potassium phosphate, magnesium sulfate, and the multivitamin, and how much will we add together. And then how much sterile water will we need to come up with that 1.5 solution, 1.5 liter solution? All right, so the way I start is on a table like this. We want a final solution of 1.5 liters. That's important. We want 17% dextrose, but we have 70% on hand. And remember, I want you to remember right now, this says 70 grams for every 100 milliliters. And so this is a recipe on how to mix, okay? Same thing with the aminosin. We're going to take what we have ordered, and then we're going to see what we actually have on hand, and then we're going to start calculating how many milliliters of this dextrose do we need to put into this bag so it ends up being a 17% solution. How much of this 10% aminosin do we need to put into the 1.5 liters to end up with a 3% solution? How many milliliters of 20% liposin do we need to put into the 1.5 milliliter bag, 1.5 liter bag, the 1500 cc bag, to end up with 2.5%, and so forth. And so the reason I'm going over this is like each of these is like an individual single question all at once, and then we'll add them all together. All right, so we'll start with the top three because they're described in percentages. We'll go back. Look. These are described as percentages, which is grams per 100 milliliters. All of these are described as milliequivalents per milliliter. So we're going to need a little bit different math down here than we're going to need for the percents. And so the first thing we're going to do is do the calculations by percentage. All right, so the order is for 17% dextrose in 1,500 milliliters, which is the same thing as 1,500 cc's, all right? And so that means if the order is for 17% dextrose in 1,500 milliliters, that means in the final solution, there's 17 grams for every 100 milliliters of solution. So this bag of 1.5 liters needs to have 17 grams for every 100 milliliters. So the first step is to figure out, well, how many grams of dextrose need to go in this 1,500 milliliter bag. And so because the question is how many grams do we need, we'll take our 17 grams per 100 milliliters, and we'll put the grams on top and the milliliters underneath. And then we'll multiply that by the 1,500 milliliter bag that we want to end up with. And that 1500 over 100 is the same as 15. And so we're going to call that a multiplier, because we're not going to do this step every time, because the aminosin is 3 grams for every 100 mils, and that'll be multiplied by the 1500. The liposin is 2.5 grams for every 100 mils, and the 1500 is the same. So we're going to end up multiplying these numbers, each of these numbers, by 15 each time. And that's from the 1,500 mils over the 100 mils. We have 1,500 mils we want to mix up, and the directions are written in 17 grams per 100 mils. All right. So that's where that green 15 comes from. We're going to use that multiplier of 15 each time. All right. So again, the order is for 17% dextrose in 1,500 milliliters of solution. And 17% means 17 grams for every 100 milliliters of solution. Well, then how many grams are we going to need in a 1,500 milliliter solution if we want it to be 17%? And so we'll take that 17 and multiply it by 15, which we did in the previous step. That means we know that there needs to be 255 grams of dextrose in this 1.5 liter solution. Okay. So how are we going to get 255 grams in this 1.5 solution? Oh, well, what we have is 70 grams for every 100 milliliters. So how much of that do we need to get the 255 grams that we need to put in the big 1.5 liter bag? All right, so how many mils of the 70% solution, which is 70 grams for every 100 mils, do we need to have 255 grams? And so here we've flipped this over because the question is how many milliliters. So we take the 255 grams, we multiply that by 100 and multiply that by 100 and divide by 70. And we end up with 364, and I put the extra digit on there, 0.3, because the book gives you all these insignificant figures that are not necessary for the calculation. And so here we need 364.3 milliliters of dextrose in this 1.5 liter bag. All right, well, if the question was just quite simply, the order reads 70% dextrose and what we have on hand is 70%, then we would need 364.3, and then the rest would just be sterile water. All right, so we would just take the 1,500 minus the 364.3. That's how much sterile water we'd need to mix up 17% dextrose in a 1,500 liter bag. However, we have multiple ingredients, and as we add the multiple ingredients, we're going to add more and more milliliters of these stock solutions. That means we're going to add all those together first before we add the sterile water. All right, so we figured out how much dextrose we need. Let's look at the aminosin. 3% aminosin in the 1,500 mils is the same thing as 3 grams for every 100 mils. So then how many grams of the aminosin are needed in the 1.5 liter bag? All right, so we want 3. And here we multiplied it by that 15 because we want a 1,500 milliliter bag, and our description is 3 grams over 100 mils, and that's going to be 15 for each of these calculations. So how many grams of aminosin are needed to fill this, or to have the appropriate amount of aminosin in this 1.5 liter bag? So we'll take that 3% and multiply it by 15. All right, so I'll tell you right now, we're going to take that and multiply it by 15, that and multiply it by 15, and that and multiply it by 15 to tell us how many grams are required in the solution. So we want a 3% solution, which is 3 grams per 100 mils. How many grams are needed in the 15 mil solution? We'll just multiply that by 15. And we go 15 times 3, that's 45 grams. So this 1.5 liter solution needs 45 grams, all right, of aminosin. All right. Well, what we have is a 10% solution. That means we have 10 grams for every 100 milliliters. So how many milliliters of this 10% solution are we going to need to come up with 45 grams? And so you take the 45 grams and multiply that by 100 mils over 10 grams, and that came from here, and we turn that upside down like we did with pickles and hamburgers to put the correct numerator on top. And what we end up was 450 milliliters of solution. And so we put that right there as the 450 milliliters of solution. Well, if all we were mixing up is dextrose and aminosin, then we would take these and add them together and then add the sterile water to come up with the 1.5 liters overall in the final solution. But we need far more calculations to finish that out. So here we're going to calculate how many grams do we need to put in the bag to have a final solution of 2.5%. All right, so we want 2.5 grams for every 100 milliliters of solution in the final. And so we'll take that 2.5 and multiply it by 15, and that will give us 37.5. Again, the 15 came from, we want a 1,500 milliliter solution, and we're using descriptions of each 100 milliliters, and so we want to amplify that. We want to expand that by 15 times, and so that's why the number of grams is 17 times 15, 3 times 15, and 2.5 times 15. And so here, 2.5 times 15 is 37.5 grams, so we want 37.5 grams of liposin in this 1.5 liter bag. All right, so how many milliliters of 20% is needed? All right, well, 20% is the same thing as 20 grams per 100 milliliters. And how many milliliters do we need to have 37.5 grams? And so we're going to take our 20 grams over 100 mils, flip that upside down, just like pickles and hamburgers. And if we take 37.5 grams times 100 mils divided by 20 grams, our grams cancel out, and we're left with 187.5 milliliters. So far to mix up this bag, we need 364 milliliters of 70%. We need 450 milliliters of 10% aminosin, and we need 187.5 milliliters of 20% liposin to come up with 17% dextrose, 3% aminosin, and 2.5 liposin. All right. Well, as if that wasn't complicated enough, now we need to mix. So the order is for sodium chloride, 15 milliequivalents per liter. That's 15 milliequivalents per 1,000 milliliters. How many milliequivalents are needed in the 1,500 milliliter solution? So if we take our 1.5 times the 15, that's 22.5 milliequivalents. And remember that 1.5 came from the 15 divided by 1,000. We're 1,500 divided by 1,000. We're increasing our recipe 1.5. And so that's why 1.5 times 15 is 22.5 milliequivalents. Goody, and that slide's correct. So since 1.5 times 15 is 22.5 milliequivalents, how many milliliters of the 4 milliequivalent solution is required to have 22.5 milliequivalents? All right, so the question is how many milliliters. So we take our 4 milliliters per equivalent and we turn that upside down, just like pickles and hamburgers, and put milliliters over 4 milliequivalents. And now we have 22.5 milliequivalents divided by 4, and that gives us 5.6 milliliters. So to have a sodium chloride solution of 1.5 liters, that is 1.5 milliequivalents per liter, we'll need to add 5.6 milliliters of the 4 milliequivalents per mil. And if this seems really complicated, it's because it is, but we have to take it one step at a time. All right, now each of these descriptions are per liter, and we're trying to make 1.5 liters. That's why all our little green multipliers are going to be 1.5. All right. So now we want potassium chloride, 15 milliequivalents per liter. That's the same thing as 15 milliequivalents per 1,000 milliliters. How many milliequivalents are needed in the 1,500 milliliter solution? So we'll just take the 1.5 milliequivalents that we have in the order, and we multiply that by 1.5. Now we know that there need to be 22.5 milliequivalents in the 1.5 liter bag. So how many milliliters of our 2 milliequivalents per milliliter, we're on potassium. Oh, good, we've already put it in. How many milliliters of the 2 milliequivalent solution is required to come up with 22.5? All right, and so we start with our 22.5 milliequivalents that we want. And our first step, of course, is to put the correct unit on top here. And we have a milliliter over 2 milliequivalents. And so that's 22.5 divided by 2. And even though you might be pulling your hair out, at this point are completely lost, I want you to see that the burger math that we're using to solve this is just as simple as the pickle and hamburger formula that we used when we first started talking about dimensional analysis. And so a lot of this just has to do with this stepwise logic. And then once you get the hang of this actually is not difficult to do, but when you do it the first time, it's a big slog, I assure you. And the questions that you'll see on the boards usually are just going to be 1 or 2 mixtures. You won't see anything this big because it takes an hour to get through it, even though we did it on an Excel spreadsheet to double check and put it on PowerPoint. All right, so that being said, the order is for potassium chloride, 15 milliequivalents for every liter, and we want 1.5 of that to make up the 1.5 liters, and so we know there's 22.5 milliequivalents of potassium chloride in this bag. And so how much of this do we have to put in that bag to end up with 22.5 milliequivalents? Well, if it's 2 milliequivalents per mil, then how many mils do we have to add to end up with 22.5 milliequivalents? So again, we take the 22.5 milliequivalents, put that on top, and we'll flip this to put our correct unit on top. The milliequivalents cancel out. We're left with 22.5 divided by 2, which is 11.5 milliliters. And so we'll put that right here in this column. And eventually we're going to add this column up because that's the milliliters that we've been putting in the 1.5 liter solution. All right, here's potassium phosphate. They want 10 millimoles per liter of solution, which is 1,000 milliliters. And remember, we're coming up with a 1,500 milliliter solution bag. And so we'll take the 10 millimoles that we want, that we have right here. We have 10 millimoles per liter. We'll multiply that by 1.5. That means we're going to put 15 millimoles of potassium phosphate in that solution. And you can think of that as milligrams. We're used to saying milligrams. We're not used to saying milliequivalents and millimoles. But it doesn't matter what kind of unit it is. If the unit they're asking for is the unit that we have, then we don't have to worry about whether it's moles or milliequivalents. Now, if you have milliequivalents on hand and the order's for millimoles, then that requires some thought. However, that's not what we see. The units being asked for is the units that we have on hand. So again, we're not making a 1 liter solution, we're making a 1,500 milliliter solution, a 1.5 liter solution. So that's where that 1.5 comes from. So if there's 10 millimoles for every liter, that means there's 15 millimoles in the 1.5 liter bag. But what we have is a 3 millimole solution. So how many milliliters of the 3 millimole per mil solution do we need to have 15 millimoles? And so we'll take our 3 millimole per milliliter solution, we'll flip that upside down just like pickles and hamburgers because the question is how many mils? And so we take our 15 millimoles, divide by 3 millimoles, and we end up with 5 milliliters. And so we put the 5 milliliters right here on our chart. on our table. All right, so now we're going to add magnesium sulfate. It's 10 milliequivalents. We want 10 milliequivalents per liter. The order is 10 milliequivalents per liter. So I know that there must be 15 milliequivalents of potassium sulfate in that 1.5 liter bag. So how many milliliters of this 4.06 milliequivalent per mil solution? I think they've tried to make things complicated for us. How many mils of 4.06 milliliters, milliequivalent per milliliters is required to have a overall 15 milliequivalents? And so if we take our 4.06 milliequivalents per mil, we flip that upside down just like pickles and hamburgers, we end up with mils on top, 4.06 on bottom. When we multiply that by the 15 milliequivalents, our milliequivalents cancel out, and we end up with 15 divided by 4.06, which is 3.7 rounded up milliliters. And so now we know how many milliliters of the magnesium sulfate solution to add. Right? I'm assuming that the 10 milliliters, that we're just giving 1.5 liters per day because they weren't specific, and I think 3.3 is too much of this, so 1.5 liters per day. And so if they're asking for 10 milliliters of multivitamin, the order is 10 milliliters per day, then we just put a 10 milliliter vial in it. All right. And so when we add all these up, the 364 milliliters of 70% solution is required to end up with a 17% solution of dextrose. 450 milliliters of the 10% solution is required to end up with a 3% solution of aminosin. 187.5 milliliters of 20% solution is required to end up with a 2.5% solution of liposin in the 1,500 milliliter bag. 11.25 milliliters of 2 milliequivalents per milliliter is required for the 1.5 liter bag to end up with a final solution of 15 milliequivalents per liter. 5 milliliters of 3 millimoles per milliliter is required in the 1.5 liter bag to end up with a 10 millimole per liter solution. 3.7 milliliters of 4.06 milliequivalents per mil is required to add to the 1.5 liter bag to end up with a 10 milliequivalent per liter solution. And then we put 10 ml vial in there to end up with our 10 milliliters of multivitamin. And so what we do is we add all these up. 364.3 plus 450 plus 187.5 plus 5.6 plus 11.25 plus 5 plus 3.7 plus 10 comes out to 1,037, which is rounded up. And so if we have 1,037 milliliters of solution that are already required, then to bring that up to the 1.5 liters, we just take the 1,500 and subtract 1,037. So to finish out the 1.5 liter solution, we have to add 463 milliliters of sterile water. And so that is the correct answer for question 29 on the ASHP quiz 3 drug calculations, because this is the most difficult question that I see on there. And if I'll make sure that you guys get the notes to these. All right, something even more fun in pharmacology and pharmacy is something called allegation. And so here we want a final solution. Here we're going to want 550 milliliters of a 25% solution. But all we have is two types of solutions. We have 45% and 10%. And maybe we can't just add one and sterile water to end up with. Sometimes we have to add a higher concentration and lower concentration together to end up with 25%. So we have a 45% solution. We have a 10% solution. How many of each of these would we have to add together to end up with 550 mils of a 25% solution? So again, how many milliliters of a 45% solution and how many milliliters of a 10% solution do we have to mix together to end up with 550 milliliters of a 25% solution. And so when they asked me to explain this in the middle of the night, I said, well, you know, I'm going to get back to you and sit down with my PowerPoints, because PowerPoints is also how I teach myself. That allows me to learn things in a very, very strict way, just one detail at a time. And so one of my favorite reasons to make PowerPoint slides is so that I can explain it concisely to myself before I attempt to explain it concisely to the camera. So again, the question is, you need 550 milliliters of a 25% solution using 45 and 10% solutions. And so in the middle here, we're going to have a little tic-tac-toe board. And on the left is a percentage, and in the middle is the percentage, and on the right of our tic-tac-toe board, those are going to be the parts. And then down below the tic-tac-toe board is going to be our final product, all right? So there's our tic-tac-toe board. To do allegations, it's just a simple game of tic-tac-toe, all right? And in tic-tac-toe, my first step, the book has a different first step, but that's how you lose at tic-tac-toe. If you want to win at tic-tac-toe, you got to start and take over the middle slot, right? And the middle slot's what you want. That very center square is what you want. You want a 25% solution. And so that's our desired concentration. We're going to put that straight in the middle of our tic-tac-toe board. And then after that, we're going to work diagonally. So we're going to do the X's, all right? All right, so in the upper right, it doesn't matter which one's higher or lower, but it makes sense to put the higher concentration in the high part. All right, so we're going to put a high concentration up there. And what we're going to do is we're going to take 25. We're going to take the 45 and we're going to subtract 25. This is going to give us our number of parts down here. Should have taken that step first. All right. But here we're going to put the low concentration there. And we're going to put the low concentration there because we're going to take 25 minus 10. And that's going to tell us the number of parts up here. All right. And that's the fun thing about tic-tac-toe. All right, so again, we're going to take the 45% that's in the upper left, and we're going to subtract the 25 that we want. And when we take 45 and subtract 25, we end up with 20 parts. All right? So we're going to need 20 parts of the 10% solution when we mix this up. And then to come up with how many parts do we need from 45, well, it's playing X's in tic-tac-toe. We have 25% solution. We want a 25% solution, and we have a 10% solution. So we take the 25 minus 10, and this gives us 15. And we'll say that's 15 parts of the 45% solution. All right. And so that's where the X's come from in our tic-tac-toe. If we take the 25 minus the 10, that gives us 15 parts of the 45%. And if we take the 45 minus the 25, that gives us 20 parts of the 10% solution. And if we add 15 parts of 45% and 20 parts of 10%, that'll give us 35 parts, just like mixing juice. 1 part of this and 5 parts of that. All right. And so this is really simple when we're mixing juice. However, getting juice to work out when we have 2 different concentrations requires a little bit tic-tac-toe. All right, so now we have a 35-part final solution, and that's why we talked about that with the juice. If you add 1 part juice and 5 parts water, you end up with 6 overall parts. All right. Here we're going to put 15 parts of the 45% and the 20 parts of the 10%. We put those together, we end up with a final of 35 parts, and so that's a very important step. So again, to belabor the point, we need 15 parts of 45%, 20 parts of 10%. And then this is figured out using the X. We put what we want in the middle. We have 45% up here, 10% down here. And if we take the 45 minus 20, we end up with 20 parts of 10%. We take the 25 minus 10, we end up with 15 parts up here. We add them together and end up with 35 parts. All right, so now you need a 550 milliliter solution. You need 550 milliliters of a 25% solution, and you're going to use 15 parts of 45% and 20 parts of 10 mils, and you want a total of 35 parts, and that 35 parts will equal 550 milliliters. All right, so how are we going to set that up? All right, we'll set it up like this, and this is called a cross product. 15 parts over 35 parts is the same thing as some unknown milliliters, x milliliters, times 55. And the way they do cross products, they tell you to multiply that times that and then do some algebra. What I'll tell you is that, see this 550 on the denominator right here? How do we make that go away? If we multiply both sides of the equation by 550, then that 550 ends up over here. And so that's what I do. When I see a cross product, I take that 550 and just stick it right there. I take this denominator and put it right there. And then we have x is equal to 550 times 15 divided by 35 here. Since I'm here, I might as well add them. Eventually we'll talk about this. I wish they wouldn't do that to me. All right, so we were talking about concentrations. Bring that back. We ended the show. I'm going to duplicate that slide because I want you to see this. And I left it out. So we'll take that. Do we need to ungroup this? Nope. So we'll take that and put that right there. And take that. Here, we'll just make that go away. We don't need that. X goes here. All right, so again, if you take the 550 mils and we'll insert a little arrow. See, we'll learn a little bit about PowerPoint. We'll take that 550 mils, we'll put it right there, okay? So that's how I do cross products. I don't go through all the algebra. And so the same thing over here with the 20 parts. We'll duplicate that slide. Duplicating slides is how you get everything to line up in the same place every time without things moving around. That's a distraction. I don't like that. So I do a lot of duplicating slides so the words and the titles end up in the same place. Because when they're moving around, that's a distraction, and that sets your tectum off in your brain to be looking for woolly beasts chasing after you rather than learning Euclidean algebra. All right, so that being said, you need 550 mils of a 25% solution using 15 parts of 45% and 20 parts of 10%. And what you want is a total of 35 parts to make 550 mils. So how many mils of the 45 will we need? And so here we're using cross product. That's how they show you. And with the cross product, all I do is take both sides and multiply both sides by 550 mils. If I divide both sides by 550, 550 mils. And so if I divide both sides, if I multiply both sides by 550 mils, this becomes a 1, and the 550 mils ends up over there. And so we take 550 times 15 divided by 35. You guys can do that calculation. That's how many milliliters of the 45% solution that we'll need. All right. Then again, we need 20 parts. If 20 over 35 is the same as x over 550, and we take that 550 and move that to the numerator of the other side. Take 550 times 20 divided by 35. That's the number of milliliters of the 10% that we need. And so this is called an allegation. This is really complicated to grasp at first. This isn't something we've been teaching regularly, but as they raise the standards for pharmacy technicians higher and higher, we have to make our math lectures more complicated. And it's really impressive because our group this semester, they really are able to have a handle on this sort of mathematics. So I'll have to step it up a notch on my end to make all that work out. All right, well, in our math in Pharm 203, we have some dilantin questions. And this one's even more complicated. Here we're going to load dilantin a little more slowly because it's a child. But here it's described like this. Did I rewrite that out? Yeah, a loading dose of an anticonvulsant medication for a child is 20 milligrams per kilogram. and we want to infuse it at a rate of 0.5 milligrams per minute. How many minutes are needed to dose the child weighing 50 pounds? And so when they ask me to explain this in the middle of the night, I'm looking at it, I'm thinking, plus when I explain things at night, I don't have PowerPoint slides, I don't have a cable TV studio, and I don't have an Elmo like this one where I can work things out by hand, so I kind of have to say, well, I guess what anybody else would tell you to do is take that 50 pounds and convert that into kilograms and plug that in here to figure out how many milligrams per minute, and plug that in here to figure out how many milligrams. Well, when I was thinking about that, I'm like, well, if we're plugging in kilograms into the equation twice, then it's going to cancel out, and that's probably a step that we don't even need to use. And so when we were solving this in the middle of the night with many fewer brain cells than I have in the morning, we took the 50 pounds, we converted into kilograms, and then we figured out how many milligrams per minute, and then how many milligrams overall, and we came up with the correct answer. However, there's a way to do this burger math style that takes out the extra steps. And so the question is how many minutes. The answer is how many minutes, and so we're going to need minute in the numerator. And here we have 50 milligram per kilogram per minute. That's a complex fraction, and we want to repair that. So there's my 0.5 milligram per kilogram per minute, and that's the way we would load it up, 50 milligrams over a kilogram times a minute, because remember, A over B over C over D is like flipping the bottom fraction and multiplying it. So if we flip the bottom fraction and multiply it, that's a milligram times a 1, and a milligram is, the minute is times the kilogram. And so when you have a milligram per kilogram per minute, that's the same thing as a milligram over a kilogram times a minute. If you're going to be doing these kinds of calculations, you're going to want to remember this step right here, because the rest of the time the computer is going to be doing it for you, and maybe somebody put something into the computer wrong, so you end up with the wrong answer. And so take the time to know that a milligram per kilogram per minute is the same thing as a milligram per kilogram per milligram over a kilogram times a minute. All right. I take the time to learn that, and take the time to learn to explain that. All right, so here I put the 50 milligrams over kilogram times a minute. I think I explained that. However, we want minutes on top. All right, and so we've taken our 0.5 milligram per kilogram per minute, and we've loaded that upside down. And so now we have a kilogram times a minute over the 0.5 milligrams. All right, so this is obviously a little bit more complicated than what we've done in the past. And we've taken our 0.5 milligrams over kilogram times a minute, and we've inverted that. Just like pickles and hamburgers, we flipped the numerator down and put the denominator up. And now we have the minute unit on top, because this was the question. All right, how many minutes? All right, so now I have a minute unit on top. Well, if we load 20 milligrams per kilogram, notice at this point my milligrams have canceled out and my kilograms have canceled out. And I'm left with nothing but 20 divided by 0.5, which is the same thing as multiplying by 2. We end up with 40 minutes. All right. So it doesn't matter how much the child weighs in this question. When we load their dilantin at 25 milligrams per minute, which is the same thing as 0.5 milligram per kilogram per minute, if we're giving 20 milligrams per kilogram, it's always going to work out to 40 minutes. So the 50 pounds doesn't even enter into this equation. This is question 23 in the third quiz of the American Society of Hospital Pharmacists board review exam, or board exam review. And so I wanted you to see this because we're doing really more complicated things with our pharmacy technicians. Their need to understand mathematics is becoming more complex. And so I wanted to, just send out a commercial saying we have a great pharmacy technician program here. And because of the intensity of the amount of information they learn, the pharmacy technician is able to grow. And we're trying to create a pathway from pharmacy technician to even PharmD at our pharmacy school in Hilo. And even if you don't go from Pharm Tech to PharmD, maybe you can go from Pharm Tech to store manager and regional manager. Maybe you can take this in the business direction. And I can assure you, the more mathematics that you know, the better you'll be at making numeric decisions in business. And so a good math background is really essential, not only for business, but for medicine, as well as being a pharmacy technician. So I want to go through those slides because I had them, and then I can use them in the future. All right, so that's more than enough for this lecture. When we come back, we'll talk about more interesting things in pharmacology. And so until then, aloha.